In this video, we're going to cover section 1.6, complex numbers. I know we're going back to the first chapter for this section, but we need complex numbers in section 8.3, and we didn't need them before now. So I'm throwing that section in right now before 8.3. So just a either reminder, or maybe this is the first time you've seen complex numbers. Either way is fine. But what a complex number is a complex number z has the form z is equal to a plus bi, where a and b are real numbers, and I is the square root of -1. Right? And normally we can't take square roots of negative numbers, but this complex number system, if we add the value I is equal to the square root of -1 to our number system, then we, in fact, can discuss square roots of negative values now. And how do we do that? Well, we do that using complex numbers, and those, again, are of the form z is equal to a plus bi. Well, a is a real number, and it is called the real part of the complex number. B is also a real number, but it is called the imaginary part of the real number. Why is it called the imaginary part? It's the part that's attached to the I, that square root of -1, which is our imaginary number. A is the real part because it is not attached to the I. Okay. So our first example we want to do is to calculate things using complex numbers. So for number 1 here, we're going to let z1 equal to 2 plus 3i and z2 equal to 1 minus 4i. First thing we want to do is find z1 divided by 3. Well, how do we do that? We take 2 plus 3i, we divide by 3. If we have 2/3 here, we split this fraction up, we get 2/3 for the real part, and 3 over 3, which is 1i for the imaginary part. So the real part is the real part is 2/3, the imaginary part is 1. All right, we can continue on. z1 plus z2 here, how do we do that? Well, we take 2 plus 3i, and we want to add to that 1 minus 4i. And how do we do this? I don't need to write parentheses here. I'm just helping us kind of see what's going on. Well, we add like terms, just as if this I was an x value. We just add like terms. So the values without the x's, 2 and a 1. So we have 2 plus 1 is 3. 3i plus a -4i is the same as 3i minus 4i. 3x minus 4x is -1x. So 3i minus 4i is -1i. And the answer here then of z1 plus z2 is 3 minus I, where 3 is the real part, -1 is the imaginary part. All right, z1 minus z2, similar thing. 2 minus 1 is 1. 3 minus a -4. Minus a negative means add, so 3i plus 4i is plus 7i. I'm going to do z1 times z2. So this is 2 plus 3i times 1 minus 4i. 2 times 1 is 2. We've got to do the FOIL method, or really what are we doing? We're just distributing, whatever you want to call this. Distributing is the appropriate term. We are distributing across, so 2 times 1 is 2. 2 times -4i is -8i. 3i times 1 is positive 3i, and 3i times -4i is, let's see here, 3 times -4 is -12, and then I times I is I squared. All right, so this is 2 minus 8i plus 3i is a minus 5i, and then I squared. What is that? Well, I is the square root of -1, so if we square that, we get -1. So this is -12 times -1. So -12 times -1 is a positive 12, plus this 2 is a 14, and then we have, of course, the minus 5i. We have one more of this type before we move on to a few other examples from this section. So we have z1 divided by z2. So we want to take 2 plus 3i and want to divide that by 1 minus 4i. Well, we have a bit of a trick, sort of, that we do for these types of problems. Every time you have a division of two complex numbers, you want to multiply by 1, essentially. But what representation of 1 do we want? We want to write the conjugate of the denominator in both the numerator and the denominator of a new value that we're going to multiply by. So what is the conjugate? The conjugate just takes the imaginary part and takes the negative of that. So 1 minus 4i becomes 1 plus 4i. And again, we're going to write that in the numerator and the denominator, because if we take 1 plus 4i and divide it by 1 plus 4i, which is just 1, so really we're just multiplying by 1 here. So we're not changing the value in any way. But because of the property of the conjugate here, and multiplying the original value times its conjugate, the denominator is going to simplify here. And we're actually going to get something a lot nicer. So we're not actually going to do any division. We're just going to multiply by 1 plus 4i over 1 plus 4i. So in the numerator, we get 2 times 1 is 2. 2 times 4i is plus 8i. 3i times 1 is plus 3i. 3i times 4i is plus 12i squared. All divided by... All right, 1 times 1 is 1. 1 times positive 4i is plus 4i. Negative 4i times 1 is negative 4i. And then negative 4i times positive 4i is a negative 16i squared. Okay, so let's simplify here. 12i squared. So I squared is negative 1, so this is a negative 12. Positive 2 and a negative 12 is a negative 10. We have plus 8i plus 3i, so that is plus 11i. All divided by 1, 4i and negative 4i cancel. I is negative 1, I squared is negative 1, so this is a plus 16, which gives us negative 10 plus 11i all over 17. Or we can rewrite that as negative 10 over 17 plus 11 over 17i. And that finishes our z1 divided by z2. We do have a couple more examples, which are not written down yet. So number 2 is evaluate the radical expression and that is going to be the radical expression negative square root of 3 times negative the square root square root of negative 3 times square root of negative 4. Well, to do this, we want to rewrite it as, what is the square root of negative 3? This is the square root of negative 1 times the square root of 3. And square root of negative 4 is the square root of negative 1 times the square root of 4, which is equal to... Well, this is square root of 3 times I times square root of 4 times I. Square root of 4 is 2 times root 3, so this is 2 root 3 times I squared. I squared is negative 1, so this is in fact negative 2 square roots of 3. And that's it for that question. Was pretty easy. We're going to have another one here. Find all solutions to the equation x squared minus x plus 2 is equal to 0. To solve something like this, if we cannot factor it, we can try the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac all over 2a. If you don't remember that, you will need to use that in this section. But negative b plus or minus square root of b squared minus 4ac all over 2a is our quadratic formula. We're going to use that. So let's go ahead and plug in our values. B is negative 1, so negative of negative 1 is a positive 1. Plus or minus square root of negative 1 squared minus 4 times a is 1, c is 2, all divided by 2 times 1. Well, what does this equal? This is equal to 1 plus or minus the square root of, this is 1 minus 8, so that'd be a negative 7, all over 2. This is 1 plus or minus the square root of 7i, right? Because this is square root of 7 times square root of negative 1. Square root of negative 1 is I, all over 2. So this gives us 1/2 plus or minus square root of 7 over 2i. And again, this is really two solutions, right? 1/2 plus the square root of 7 over 2, and the other one is 1/2 minus the square root of 7 square root of 7 over 2 times I. I think I said that wrong, so I'll restate it just in case. This is 1/2 plus square root of 7 over 2i, and 1/2 minus square root of 7 over 2i. We have, that was question number 4 now. The previous one was 3. Okay, so the last one we want to find I to the 72nd power. All right, that looks scary and gross. It's not. So we can think about this in a pretty easy way. What is I? I is the square root of negative 1. What is I squared? Well, we take that and we square it and we get negative 1. What is I cubed? That is I squared times I, which is I squared we said was negative 1. So this is negative 1 times I, or just negative I. What is I to the 4th? Well, this is I squared times I squared, which is negative 1 times negative 1, which is 1. And then what is I to the 5th? That is I to the 4th times I, but I to the 4th was 1, so this is just back to I again. What does this tell us? Well, when our exponent was, if we have exponent 0, I to the 0 is 1. If we have exponent 4, I to the 4th is 1. If we continue along this pattern, we should see that I to the 8th would also be 1. I to the 12th would also be 1. So every time we add 4 to the exponent here, we just get 1. And so really, I to any power, any integer, positive integer power, just rotates between square root of negative 1, negative square root of negative 1, and positive 1. And we just cycle through those 4 solutions. So what we want to do is we want to find out, is 72 divisible by 4? And if not, what is the remainder? Or really, what is the remainder of this value, this exponent, when divided by 4? Well, 4 goes into 7 one time. And once to 4, drop the 2. Well, sorry, 0, subtract 3, drop the 2. Right, 4 goes into 32 18 times. Or sorry, 4 goes into 32 8 times, so 4 goes into 72 18 times. And what does that mean? It goes in there evenly. So we get remainder 0. Looking back over at this list, if we have I to the 0, which I didn't write out here, but I'll do that now, we get 1. We have I to the 4th, we get 1. But what is the remainder of 4 when divided by 4? That remainder would be 0. So again, we're at remainder 0, and the solution was 1. At I raised to the 8th power, again, 8 divided by 4 would have a remainder 0. I to the 8th was also 1. So anytime we have remainder 0, that value is just 1. to continue along with this idea, if I had asked for what I to the 73rd was, what would that be? Well, this would be I to the 72nd, which we just said was 1 times I, so we would just get I. So again, we kind of just rotate through this list. I to the 74th would have been I squared, which is -1. I to the 75th would have been I cubed, which is -I. And I to the 76th would be the same as I to the 0, which is 1. Again, we were just asking for what I raised to the 72nd was, but we can calculate any I raised to a positive integer value in this way. And that's it for the video from section 1.6 on complex numbers.